And now let's start. So far we covered different topics related to the circuit analysis. But what if I give you something like this, a circuit like this one, a voltage source, let's say Vs, connected to a resistance R1, R2, R3, R4, R5, R6, R7, R8, something like this. And then I will ask you to find for me this current I. That looks scary, to be honest with you. And to do that, as we said, okay, we have to assign a current in every branch. So this would become I1, I2, I3, I4, I5, I6, I7. So we have 7 unknowns plus I, so 8 unknowns. It means that I will need 8 equations. And that's really very math intensive to be able to solve this. But what if I can reduce this whole circuit and make it something like this? My Vs as it is, and instead of all these resistors, I will have just one. I will call it R equivalent. So this resistance is equivalent to all of this. So if I want to find I, it's basically I Ohm's law, Vs divided by R equivalent. So this is a very good shortcut. If we can combine resistors together, reduce the circuit dimension, then that can help us a lot in the solution. And that is the topic of our lecture today. So we'll talk about two different connections that can be used or it is used in the circuit and can be used to reduce the circuit size. The first one is a series circuit. And here I'd like to stress on something very important, is how to know if the resistors are connected in series or in parallel in the coming slides. This is very crucial because if you mixed up the connection, then you will get up the wrong results. So here let's see the definition very clearly. Two elements, by the way, they could be any two elements, but we are mainly using it for resistors, are connected in series if there is no other element connected to the node joining them. So if these two elements are joined at one node and there is nothing else connected to that node, then we identify these two as in series. For example, A and B are connected in this node, and there is nothing else connected at this node other than A and B. So we can say that A and B are in series. B and C also in series. They are joined at this node and nothing else connect to node number 2. So B and C are in series. Now since A and B in series, B and C also in series, then we can say A, B, and C, all of them, they are in series. Another way to look into it, see this current IA, IB, and IC. This current is a flow of electrons. So this current is exactly the same as this current. It does not split. There is no, at this connection, there is no other elements that the current will be splitting between two different paths. It's just the same path. So this current in IA is the same as IB, as the same as IC. So these are the two criteria you can use. You can use one of them, but I prefer the first one because will really give you an easy way to tell that if these elements are connected in series. So now let's derive what will be the equivalent resistance if they are connected in in series. So here we have V1, we have a current I and have a voltage. So we can see that V1 is nothing but I times R1. And V2 with the polarity, now we understand this polarity because the current enter the terminal. So it becomes plus minus. So V2 now here is nothing but I R2. And finally, V3 is equal to I R3. And here I come back to the fact that these are in series as an indication that they are in series. They have the same current I. All of them have the same current I. Now, if I apply KVL here, your V equal to V1 plus V2 plus V3. This is KVL. V1 plus V2 plus V3 minus V equal to 0. Summation of voltages in a closed loop is equal to 0. So V is equal to V1 plus V2 plus V3. Or I can say that V1 is I R1 plus V2 is I R2 plus V3 I R3. So I can say here V is equal to I times R1 plus R2 plus R3. So if I want to replace these three resistors with R equivalent of those resistors, so we have I equal to R equivalent. So I can substitute this circuit with one resistor. I will call it R equivalent, and this is your I. And this R equivalent, as you can see here from definition, is equal to summation of all the resistors in series. So basically, if you have resistors connected in series, you just add them, and then you will have one equivalent resistor that sum the values of all other resistors. So this is the first connection, which we call it in series. And here all the division. The second one is what we call as parallel connection, and there is always sort of an analogy between the two. In the series connections, it is shared one node. We'll see here what they shared. In the series connection, they have the same current, and here we will see they have the same watt. So two elements, again, let's clearly see the definition, are connected in parallel of if both ends of one element are connected directly to a corresponding end of the other. Each element, it has two ends. So for example, if I have a resistance here, it has two ends, end A and end B. So this resistor R1, it is connected in parallel with another resistance R2 if both ends are the same. They share the same ends. So if you look to A and B, now we agreed that this node and this node are the same. Why? Because there is no any element here. So this node and this node is the same. Also here, this node and this node is the same. So you can see that A and B share the same two nodes. Their two nodes are shared together. Then A and B, we call these two are in parallel. Let's look to D, E, and F. Again, this point, this, and this, all of them are exactly one point. Why? Because there is no elements between this point and this point, or this point and that point. Same thing here. So these three elements, D, E, and F, they share the same two nodes. So these three elements are also in parallel. Now, the question is, how about C? Is B and D connected in parallel or not? This is very important to understand. Okay, per definition, the two elements, they have to share the same two nodes. So B and D, this node is exactly the same. So they share the bottom node. But the upper node, they don't share it. This point, if I call this point as A, this is B. A and B are not the same. Why they are not the same? Because this element is in between. So this point is different than this point. So it means that B and D is not in parallel. So that's very, very important to understand and be able to deal with, so that you will not mix series and parallel. And in many cases, they are neither in series or parallel. That's very important to understand. Now, if they are in parallel, then they have the same voltages. So if you look here, if the VA, VB, and VC with this polarity, then VA is equal to VB, but it's equal to minus VC, because the polarity of VC were reversed, or was reversed. So this is why we can say that VA equal to VB and equal to minus VC. So parallel resistors, they have the same voltage. Series resistor, they have the same current. Series resistor, they share only one node and nothing else share this node. Here they share two nodes. However, you could have multiple also if they all of them share the same two nodes. Now let's find the equivalent resistance here. How to find the equivalent resistance if they are in parallel? Now we say that all of them, they have the same voltage. So across R1 it is V, across R2 it is V, and across R3 it is V. So it's the same voltage everywhere. So we can say that I1 is nothing but V divided by R1, Ohm's law. I2 is equal to V divided by R2. I3 is equal to V divided by R3. So V is common between all these currents. Now, if we apply KCL here at this node, your I, so applying KCL, so you will see that your I is equal to I1 plus I2 plus I3. So I can substitute here. So we can say that your I is equal to I1, which is V over R1, plus I2, which is V over R2, plus I3, which is V divided by R3. So now I can take common factors. Your I is equal to V 1 over R1 plus 1 over R2 plus 1 over R3. Okay. So we can say that here I is equal to 1 over R equivalent times V. I is this I, V is V. So 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. There, R equivalent is equal to R1 plus R2 plus 3. Here, 1 over R equivalent equal to 1 over R1 plus 1 over R2 plus 1 over R3. So that's how you find the R equivalent. Now, if we have two resistors in parallel, this is a special case. So if I have two resistors only in parallel, R1 and R2, and I want to find R equivalent. So the same thing, 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So let's collect and let's add these terms together. So we'll have here R1, R2 over R1 plus R2. So it means that your R equivalent is equal to, take the inverse of this. So it becomes R1, R2 over R1 plus R2. So you can see here the equivalent resistance is equal to the multiplication of the two resistors in parallel divided by their summation. So whenever you see two resistors in parallel, you multiply them and then you divide them by their summation. You will get the R equivalent. If you have two, if you have more than two, then you have to say 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. Now, what if I have this scenario. I will have R1 and a short circuit in parallel, and I want to find the R equivalent. Now we know for the R short circuit, R is equal to 0. There is no resistance. So we can say that R equivalent, again, the multiplication of the two. So 0 times R1 divided by 0 plus R1, which is equal to 0 divided by R1, which is equal to 0. So the equivalent of this will be just the short circuit. So it means if I have a short circuit in parallel with a regular resistor, the short circuit will dominate. It will remove completely R1 as if it doesn't exist. How I can look to it from a different angle? Assume that, yes, any short circuit is equal to 0. Any short circuit here, it has a resistance is equal to 0. So if I have a current I, we'll have here I1 and I2. But because this has no resistance, the current tends to go to the path with the lowest resistance. This one has certain resistance. This one has no resistance at all. So the whole current will be going here, and I2 will equal to 0, and I1 be equal to I. So this will have no current to flow through it, so as if it doesn't exist. The whole current will be going here in this short circuit, and this as if it doesn't exist. So it's very important to understand this important concept about short circuit in parallel. Now let's go to the real deal, and let's start to do resistors. Whenever this is I said KCL, KVL, Ohm's law will be one question in the midterm. Finding an equivalent resistance will be another question in the midterm. So it is very important to understand this concept, how to deal with resistors. So before we go in details, let's have the strategy. So here you will have a combination of resistors, and usually you have like 2 points, A and B, and you will be asked find your R equivalent. Now, if I come from this side, is R1 with R2 in series or in parallel? Let me see here if you can answer this question. In series, 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 series. No one says in parallel. Come on, guys. All of you guys saying series? Neither. Yeah. Okay. 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 Let's go up, 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 up. Dominic. Okay, Dominic. That it's neither. Before that, Jessa also said neither. Okay. It is neither. Why neither? Okay, and this is why I want to stress on, before you find the resistors, we need to understand, very important, how I can judge. Now, R1 and R2, they share one node. So they don't share the two nodes, so they can't be parallel. Now, they share one node, but the question is, are R1 and R2 the only two elements sharing this node, or there is another element sharing this node with them, which is R3? So this node is not only shared by R1 and R2. So it means that R1 and R2 are not in series. So this is very, very important. Okay, so this is the first thing. Second thing, it's always in these type of questions, you start from this side, not from that side. Usually from this side, you cannot identify anything in parallel or in series, but from this side. So if you look to this side now, R3 and R4, what do you think, guys? Are they connected in series or in parallel? R3 and R4. R3 and R4. So series, 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 series. Okay, anyone said neither? No, all in one. Okay, okay, excellent, excellent. Yes, they are in series. Why? Because they share this node. This node is shared between them. Okay, so this is the shared node. And nothing else is connected. So what we do now, Once we identify these two are in series, then we will redraw the circuit with a reduced circuit. So these two will be connected together. So R3 and R4 are in series. So I will call this is R equivalent 1, which is equal to R3 plus R4. Because they are in series, we just add them. So this is equal to 5 plus 15. And this gives me 20 ohms. So now when I redraw the circuit now, so this is my 10 ohm, nothing changed. This is 20 ohm, I didn't touch it. But now R3 and R4, I become one resistor, and its value is equal to 20 ohm. Okay, now how about this 20 ohm and R2? This is R2 and this is R equivalent 1. What do you think, guys? Parallel, 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 parallel. Excellent. So these two are in parallel. Why? Because they share the same two nodes. This node and this node are shared together. So they are actually in parallel. Okay. So we will consider these two together. I will call them as R equivalent 2, which is they are in parallel. Because they are in parallel, how you find them? You multiply them and you divide by their summation. So it becomes 20 times 20 divided by 20 plus 20. And this is equal to 400 divided by 40. And this gives me 10 ohm. You will realize later on, once you have two resistors in parallel and they have the same value, both of them, the equivalent is half of this value. So now let me redraw the circuit. I will have the R1, which is equal to 10 ohm, and I will have R equivalent to R equivalent 2, which is another 10 ohm. And I want to find the total equivalent between these two, between point A and B. And obviously now these two are in series, so the total R equivalent is equal to 10 plus 10 equal to 20 ohm. So what does this mean? It means I can replace this whole mesh of resistor with only one resistance equal to 20 ohm. Let me address any of your questions if you have any here. Okay. How do you choose the position on the resistor? Why is not in the top instead of the side? On the top, I don't understand the question, but if you mean why we go from this side, not from this side, because in this side you can identify easily the resistors who are connected in series and parallel. If you come, these 2 points are floating. They are not connected to anything. So it will be very, very hard to identify between these two points, anything in series or in parallel. Okay, let me see here. Okay, okay. Let's move on. Okay, now we start getting things more interesting. Okay, so when I see here, we want to find the equivalent resistance between A and B. And again, if you come from this side, it will be very hard to identify anything because the 2 kilo ohm is neither in series or in parallel with any of these things. It's in series maybe with the whole thing. So let's come from this side. Now, when we come from this side, clearly the 1 kilo, the 2 kilo, they are these two together. They are in series. Why? Because they share one node and nothing else sharing these two nodes. So I can add these two together and this becomes equal to 3 kilo ohm. So if I redraw the circuit here, 4, 2, 2, it looks complicated, but it's not actually. Once you do it one by one, it becomes very straightforward. So this is 6, 10. Now these two together, we have here another 6. So these two becomes 3. Now this 3 and this 6, they are in parallel because they share this node and they share this node. So they are in parallel. So the 3 and the 6 in parallel, 3 parallel with the 6. So you multiply them, divide by their summation. This is equal to 2. Okay, so now I will again redraw the circuit. So I will keep doing this every time I did combine two resistors, redraw the circuit and see how your circuit start to look like. This is make it you much easier, and it will minimize the confusion that you might get. And you write the value. This is 9, this is 6, this is 2, this is 6, and now we will have here is 10, and these now becomes 2. Now things becomes clearer and clearer. So these two now they are in series. Okay, so this becomes 12. So again, I'm doing it very slowly so that you can follow with me. 4, because this is still new topic for you guys. 2, 6, 9, 6, and this becomes 12. Now this 6 and this 12, they are in parallel. 6 in parallel with 12, you have here the answer still there. So this becomes 4. So all of these becomes, I will just remove them and I will call them 4 kilo ohm. So we have here 2, 2, 4, 6, 9, and now everything here becomes 4. Now this 4 and this 2, they are in series, with they share only one node. So this becomes 6. Now this is 6 in parallel with this 6. Then you will have one resistor that it's equal to 3. So what we will have here, 2, 4, 9, and then I will have here 3. Why 3? Again, 2 plus 4, they are in series 6. Now this whole thing is 6, is in parallel with this 6. 6 in parallel with 6, we said that we have two resistors in parallel, that they have the same value, then the total, yes, the diagonal will go away. Now because we have all of this here together, this becomes 3. Now this 3 and this 9, they are in series. So this becomes 12. So we'll have here 2, 4, and 12. This 12 and this 4, they are in parallel. So 12 in parallel with 4. This is 12 times 4 divided by 12 plus 4 will equal to 3. So this is becomes 3, 3 in series with 2. So the total becomes 2 plus 3 is equal to 5 kilo ohms. And this is the final answer. I am having some questions here. Let me address them before we go to any. Okay. How come the 6 are in parallel since there is a diagonal? Okay, I think you guys have some problem here. Let me revisit this. Okay, let me take out the eraser. Let me remove all of those. We do it slowly here. Okay. Okay. Okay, so here we agree that we have 2, 4, 9, 6, the diagonal element, and this becomes equal to 6. 2 plus 4, 6. Now this 6 and this 6, both they are in parallel. They share this node and they share this node. So they share both nodes. This is why I said these two are in parallel. So the 6 in parallel with the 6. So this is equal to 3 kilo ohm because they are equal to each other. And when they are in parallel, they are half. Or you just say 6 times 6, 36 divided by 6 plus 6 is 12. 36 divided by 12 is equal to 3 kilo ohm. So now we will have this. This becomes 2, 4, 9, and this is a 3. Now, the rest, as I did, these two, they are in series. Comes 12. 12 in parallel with 4, 3. 3 plus 2, we give you the 5 kilo ohms. Let me do it in a fast pace a little bit. Let me just erase everything here and let me show you the answers here. So this is 3 kilo ohm, these two together, 3 kilo ohms. With this 3 and the 6, they are in parallel. So 6 and 3 are in parallel. And then 6 and 3, this is 2 with the 10, then becomes 12. 12, so we have here 12 in parallel with the 6. You get the 4 kilo ohms here. And then the 4 and the 2 becomes 6. So we have here 6 and 6. They are in parallel. So this becomes equal to 3 in series with 9 is 12. 12 with the 4 get you 3. 3 plus the 2 we get you the 5 kilo ohm. So this is something that you expect. Okay, how much work we should show in the exam? The more you show, the better. Why is that? Because to the partial, if you try to go for some shortcuts or you solve in a piece of paper that you don't show and then your final answer is wrong, then it will be difficult to get partial mark. Now, do you have to show all the circuits? No, you don't have to show all the circuits. You could if you want, but at least you identify, okay, I'm adding this. You can write down. If you can visualize it. Why I'm redraw the circuit? Because it becomes easier for you if you don't I mean, to visualize, it's easier to draw it every time. Then you can see the difference. So here, this is easier one. So you can see here, this 3 and this 6, they are in series. So become 9. So this becomes 9. Okay. This 9 and this 18, they are in parallel. So 9 and 18, this becomes equal to 9 and 18 becomes parallel, becomes 6. So everything here becomes 6. All of this is equal to 6 kilo. This 6 with this 6 with this 10, all in series. So you will get, this is the total is equal to 6 plus 6 plus 10, which is 22 kilo ohm. It seems that diagonally you have a problem with it. Let me just do one thing here so that you guys, you can visualize what I am talking about the diagonal. If you understand this, then this hopefully make sense to you. So if I have a circuit like this, and then something like this. Okay. Okay. Now this circuit, I can, if I call this is R1, R2, R3, and R4. Now I can have this as R1, R2. This R3 is nothing but like this. R3 and R4. Okay. So how comes, and this is if there's a short circuit, it will be a short circuit. If this does exist. So This is one node which connected R2, R3, and R4. This is the same node connecting R2, R3, and R4. And the bottom node is connecting R3 and R4, and the short circuit connected to R1. So these two circuits are exactly the same. Okay, but this is maybe easier for you to visualize. So having something like this in like a diagonal, it doesn't easy now. It becomes easier for you to visualize it this way. So if they make them straight lines, is easier for you other than this. But basically, you see these R3 and R4, they share this node and they share this node. So they are in parallel. So you can add them to only one resistance. The last thing, the last shortcut we'll talk about today is what we call a voltage division. Okay, what is a voltage division? What if I have this circuit? I am only interested in the voltage in R3. That's it. I have no interest in anything in this circuit. I don't need to go and find anything in this circuit. So my only interest is only R3. Why I have to go and solve the whole circuit, find the current, then find the voltage? So is there any shortcut for that? And this becomes the voltage division. So today we talk about resistor reduction, and then we have two concepts, one called voltage division, the other one called current division. So these are somehow shortcuts, but they are derived from KCL and KVL, as we will see. So here if we apply KVL here, okay, we did that before today. We said I R1 plus I R2 plus I R3 is equal to V total. We did the same KVL before. This is your V1, V2, and V3. So your I basically equal to common factor R2 R3 equal to V total. So your I will equal to V total over R1 plus R2 plus R3. This is your I. So if I want to find V3, okay, so what is V3? V3 is nothing but I times R3, or is equal to V total times R3 over R1 plus R2 plus R3. What if I want to have V1? It's IR1, which is equal to V total times R1 divided by R1 plus R2 plus R3. Okay, so what? Okay, let's come up with the rule. If we have resistors connected in series, they have to be in series. Voltage division is only applied to resistors in series. So R1, R2, and R3 with the voltage source, all of them connected in series. If they are not in series, then we cannot talk about voltage division. So the voltage source along with the resistors, they have to be in series. Once this is the case, then the voltage across any element is equal to the main voltage source, times the resistance of that voltage of interest. Meaning, if I want to find V3, it's equal to R3. So the V total times R3. If I want to find V1, it is your V total times this R1 divided by the summation of all resistors in series. R1 plus R2 plus R3. So I don't need to do any of this derivation. I can directly in one shot find this specific voltage. And let's have very simple example here. I want to find V1 and V4. Straightforward. So V1 using voltage division is equal to the V total, which is 15 volt, times this resistance of interest, R1. Why R1? Because I want to find V1. So it is 1 kilo divided by the summation of all resistors, 1 kilo plus 1 kilo. Yes, the voltage division only works if the voltage source and the resistors are in series. Otherwise, it doesn't work. Plus 2 kilo plus 6. So this becomes 15 times 1 divided by 10. Now here kilo, this kilo will cancel. So this becomes 1.5 volt. If I want to find V4, it's equal to the same thing, 15 times 6 kilo divided by 1 kilo plus 1 kilo plus 2 kilo plus 6 kilo. So it's equal to 15 times 6 kilo divided by 10 kilo. So the kilo will cancel, and this gives me the -9 volt. So I don't need to apply KCL and or KVL and Ohm's law. It's one shot, and this is called the voltage division. So it has to be in series to be able to apply. Let's see. This is the last thing I want to see today, but let me see if you have any other questions. How come the 6 are okay? We finished the diagonal. Okay, let me see the questions. How much would like want us to show on the exam? Okay, we'll finish all of this. Does the voltage only work with series? Yes, only for series. If you turn your circuit into a series circuit by what we're just doing, we can, yes, and we will see this. We will have a circuit that is not really in series, then we will convert it to a series, then we can apply the voltage division, and that's what we're gonna do in our class tomorrow. So what we'll do tomorrow, we'll do more harder examples. We will do something called the current division before that. So the current and the voltage division together, we can solve many circuits in a much simpler way. And then we'll learn about something very, very important, which is the Wheatstone bridge. It's very important to understand it. I will explain it tomorrow, and you will need this circuit in your coming lab. So please, it's a very important class that you have to attend so that you can attend you can understand the labs in a much better way. So we'll talk about the Wheatstone bridge in the two modes, the balance mode and the unbalanced mode. And then your lab experiments will be capitalized on your understanding of this concept. Let me stop the recording. Last time I think the recording did not